All right, we're in 9.4 now, and we're looking at models for population growth. And in this section, we're only talking about the two models for population growth that we've already discussed a little bit previously in Chapter 9. So in particular, we're looking at what's called the law of natural growth, which is the first one that we talked about, and then we're looking at the logistic model. It's a relatively short section. There's some derivations of things that we do here, and then we're going to look at one example where we use our logistic model at the very end. But not quite as much in this section to talk about as previous sections. So just to recap, back in 9.1, we said that if P represents the size of a population, and by population, we're talking about any organism that's capable of reproduction. So it could be humans, bacteria, field mice, whatever. We said that as the size of your population increases, then the number of organisms capable of reproduction is increasing in that process, which means the rate of population growth is likely to increase along with the size of your population. So that means that dp dt should be increasing as p increases, and one way of modeling that relationship is to say that those two quantities are proportional to each other, which symbolically is written this way: dp dt equals kp for some constant k. And generally k we're going to assume to be positive, because otherwise an increase in one variable would actually cause a decrease in the other. So this was the kind of most basic population growth model that we talked about. And it's based only on that one assumption, that as your population increases, so does the rate of growth of your population. And because of that, we call this the law of natural growth. Now, it turns out that despite this name, it's actually not as natural as it initially seems, because in nature, population growth is affected by more than just the population size. There are things that can stunt or slow the growth of a population, such as members of the population dying over time, and consumption of resources in your environment. So if an environment is overpopulated, you can exhaust your resources and starve out that population. Those sorts of things occur in reality, and so this one assumption for population growth is not really sufficient. Our logistic model will take more into account. But we saw back in 9.1 that solutions to this thing can look like P equals C e to the kt. We verified this by checking it against our differential equation and seeing that this was satisfied by these equations, or these functions. What I want to do here is show that this family of solutions to this differential equation consists of all possible solutions to this differential equation. In other words, there aren't other solutions that look different than this. These are the only ones that exist. We can do this by using what we learned in the previous section. This is a separable differential equation. Notice I can divide both sides by p, and I can multiply both sides by dt, which gives me dp over p equals k dt. And then I can integrate both sides of that, which is fairly straightforward to do. On this side, I get the natural log of the absolute value of p. On this side, I get kt plus my constant of integration c. And then I can take e to the power of both sides for the purpose of canceling that natural log out, leaving me with just the absolute value of p here equals e to the kt plus c. And then we've seen before that you can use an exponent property to split this up into e to the c times e to the kt. That e to the c there is just some arbitrary constant. So I'm not even going to bother calling it e to the c. We're just going to think of that whole thing as just some constant. In addition to that, this absolute value of p here, you can eliminate that absolute value as long as you write a plus or a minus here. That accounts for the absolute value here. But again, that e to the c is just some arbitrary constant, and putting a plus or minus here is just turning that arbitrary constant into some potentially different arbitrary constant. So all of that together, we're going to call that a instead of the plus or minus e to the c there. It's just simpler that way. And then the e to the kt will stay put. So p is equal to a e to the kt. which is essentially the form that this takes. I'm using a C instead of an A, but again, that A and that C are just arbitrary constants. Now, if you use the initial condition that we stated up here, which says that at time 0, our population is P naught. So in other words, P naught represents your initial population. Then you can use that initial condition here, plugging 0 in for T, so that this becomes A times e to the 0, or just A, which means P naught, which is what we would have on this side when checking our initial condition, is equal to A. So we can substitute P naught in for that A right there, and we end up with this. The solution to this IVP right here, here's your population growth model, here's your initial condition, is this. The population is equal to your, the population function as a function of t is equal to your initial population P naught times this exponential e to the kt. So that is now something that we can just use anytime we're asked for asked to apply the law of natural growth to some problem. We don't need to go through this derivation every time now. Let's look a little bit more closely at this constant k that's appearing here, because there's a way of interpreting that that's kind of useful. If you just go to the original differential equation, you can solve that for k by dividing both sides of this by p, which would give me k equals dp dt over p. Now that's a ratio, and we can interpret it as a rate. But what would we interpret that as specifically? So up here in my numerator, I have a rate of growth in my population. And down here, I have the population size itself. So a way of thinking about this is that K represents the rate of change in our growth rate. So it's a rate of change in a rate. But relative to the size of your population, because we're dividing by p. So because of that, k is oftentimes called the relative growth rate of the population. It's not the same thing as the actual rate of growth, dp dt itself. It's dp dt, but scaled by p, or relative to p, hence the name. Okay? We're not going to spend any more time talking about the relative, or the law of natural growth, which is what we just kind of arrived at with this result here. We want to spend the rest of our time looking at a more realistic population growth model, the logistic model, which we have also talked about. So if you remember back then, the idea behind the logistic model was that populations don't actually grow exponentially indefinitely. Exponential growth skyrockets in a relatively short period of time, and it proceeds on towards infinity. There are no populations out there with a population size that's approaching infinity. It just doesn't happen. Like we said, there's things that restrict population growth. So the logistic model takes that into account, and basically, as a recap, it says that any population within a particular ecosystem or environment or whatever it is has what's called a carrying capacity, which basically represents a maximum number that population size can hit, or an upper bound for your population size. And we also talked about how if our population, starts at a value above that carrying capacity, then the population won't grow, it will decline. Members will die off until we kind of get back to that carrying capacity again. So that carrying capacity, when we took it into account, we also needed to consider this initial condition, this original assumption that population growth is proportional to population size. We still wanted to kind of use this, but instead of saying that population growth is exactly proportional to the population size, we put an approximately symbol here. So we exchanged that equals for an approximate symbol, or approximation. And we said that approximation basically holds only when p is relatively small. Okay? When we put those conditions together, we arrived at this differential equation. So dp dt is equal to kp times 1 minus p over m. And we sort of talked through the reasoning behind this. We don't need to go through all that again. This dE, this differential equation, is also separable, because if you notice the p times this entire thing in parentheses here, I can divide both sides of this equation by all of that, and then multiply both sides by dt, and I will have separated variables by doing that. That's what we're seeing right here. So there's the dp over all of this stuff that we have here. equals k dt. Now what I want to do is integrate both sides of this like we do when we separate variables. And there's a little bit of a shortcut that we can, not a shortcut, but a little bit of work that we can do on this integrand to make that work out the way we want it to. So what we're going to do is we're going to take that integrand, 1 over p times 1 minus p over m, and get rid of the m in the denominator here, which you can do by multiplying the numerator and denominator by m. That m would distribute into here and eliminate that denominator, giving me a p here and then an m here. So it becomes m over p times m minus p. Okay. Now I'm not going to go through the work to show this, but I would encourage you to, as practice, do the work in this next step. This expression is a perfect candidate for a partial fraction decomposition because I have a function of p times another function of p in my denominator. They're linear polynomials of p. You can think of it that way. Remember, m is a constant. If you do a partial fraction decomposition on this, you're going to get that it's equal to 1 over p plus 1 over m minus p. Again, verify that. Do the work to show that this is the case. It's good practice. But now that we know that, I can take the original integrand up here and write it as a sum of those two terms, which when I integrate will give me two natural logarithms, the natural log of the absolute value of p minus the natural log of the absolute value of m minus p. And then over here, my k dt is going to become kt plus some constant c once I integrate. Next up, I want to use one of those properties of the natural logarithm where if I have natural log of something minus natural log of something else, I can combine them into a single natural log where I divide those two arguments there. Okay. Now you're going to notice here it's getting from here to here. There seems to be an issue, and what's happening is I'm seeing the wrong thing in the numerator and the wrong thing in the denominator. If I combine these on the left-hand side, I should be seeing p over m minus p, but I'm actually getting the reciprocal of that. But if you also notice, the right-hand side has changed as well. So the right-hand side, it looks like I multiplied it by a negative. So what's really happening here is I would have had the natural log of p over m minus p here equals kt plus c, but then both sides were multiplied by a negative 1. And if you multiply a natural log by a negative 1, remember you can take that negative 1 and make it an exponent here. Raising this to the negative 1 power just takes the reciprocal, which is why we're seeing this. And then distributing this negative in here would give me this. Okay, there's a reason why we're doing that. It's going to help with some simplification later. But at this point, we can eliminate the natural log by taking e to the power of both sides. So we're seeing that here. Once again, I can use an exponent property to write this as e to the negative c times e to the negative kt. And I'm going to think of that e to the negative c as just some arbitrary constant. And I'm not going to worry so much about it looking like e to a power of something. Also, in the previous case of our previous growth model and the derivation that we did, we can get rid of the absolute value bars by putting a plus or minus in front of this e to the negative c. But then we think of the plus or minus e to the negative c, that whole thing is just some arbitrary constant, which we call a. So here is all of the work that we have done to simplify things down. Okay, m minus p over p equals a e to the negative kt. So we're going to keep going with that. Okay. This is explaining where the a come from. We just talked through that. Now, in fact, let me go like this so we can kind of see where we left off. There we go. So here's where we left off. Notice I can split this up into m over p minus p over p, or m over p minus 1 equals a e to the negative kt. Okay, so now that I've talked through that, we'll just use this page. The next thing I could do is add a 1 to both sides and then take reciprocals of both sides so that this becomes p over m equals the reciprocal of 1 plus a e to the negative kt. That's what we're seeing right here. Finally, multiplying both sides by m gives me p equals m times or over 1 plus a e to the negative kt. We've isolated p, which was really the goal this whole time. We wanted to solve for p so that we have a function that we can use as a solution to that differential equation. Now there's a second step to this, which is using your initial condition. So again, we're going to assume that we have an initial population of p naught, meaning p of 0 equals p naught. So if I plug a 0 into the right-hand side of this, I'm going to get m over 1 plus a. And on the right-hand or the left-hand side, I would get p naught. So if we try to solve that thing for a, because that's that arbitrary constant that we want to know what to set that equal to in an actual problem. You can go through a few algebraic steps to solve that. You would get here, a is equal to m minus p naught over p naught. Do the steps of, the steps that go into solving this too. So there's some algebra that just took place and I didn't write it down. I didn't put it in the notes. Go through that algebra yourself. It's really good practice, okay? So this is our population growth model in the logistic equation. So we can just call this the logistic model for population growth. Again, P of t is equal to m, your carrying capacity, over 1 plus a e to the negative kt, where a is given by this. So you can compute a as long as you know your carrying capacity and you know your initial population. Typically, a problem will tell you both of those things at the very beginning. So you can compute a right from the very beginning. That would mean that the only real unknown constant in here is that k, and usually we can do some work in the problem to find that. In fact, I'm going to show you in the next problem that you can solve problems with a logistic model without ever knowing what k is directly, as long as you're kind of clever about it. So an observation that's made here, which is really important, it says, notice that the limit as t approaches infinity of p of t is equal to m. What that means is that the population doesn't skyrocket off to infinity as time passes. But as time passes, your population is going to be approaching that carrying capacity. It's never going to reach it under this model anyways. To verify that, the only place in our model where t is appearing is right here. So remember, k is a positive constant. So putting a negative here means that this is a negative coefficient on that t. So the negative kt here, if t is going to infinity, then that exponent is approaching negative infinity, which means e to that power that's approaching negative infinity must be going towards 0, which zeroes out this entire term. I'm left with m over 1, which is just m. That's where that's coming from, okay? So let me talk you through one example where we use this logistic growth model just to give you a sense of how to work with the results that we just came up with. So here is the situation. It says there's initially 1,000 deer in a mountain range with a carrying capacity of 10,000. After 1 year, the population grows to 2,500. What will the population be after 3 years? Now, it's not telling us use the law of natural growth or use the logistic growth model, but the fact that it mentions a carrying capacity, which we only take into account when we're using the logistic model between the two that we've talked about, that suggests that we want to use our logistic model here. I don't need to go all the way back to the differential equation. I don't need to solve that or anything like that because I've done the work here. So I'm just going to use these results. Okay, in this problem, our carrying capacity M is 10,000. So I'm going to just write that down. Okay, and then the value A that's mentioned here is our carrying capacity, so 10,000, minus our initial population. So this tells me that there's initially 1,000 deer. Our initial population over the initial population. That would be 9,000 over 1,000, or just 9. So taking these things together, my population growth model, or my population model rather, P of t, is equal to M, my carrying capacity, so 10,000, over 1 plus A, which we found was 9, e to the negative kt. Now I can't use this model for anything yet because I don't know what k is. So there's still kind of an unknown floating around in there. That's where we start using the other information given to us in this problem to see if we can solve for this. So now that I know this, I'm going to look at the next sentence. After 1 year, the population grows to 2,500. So P of 1 is 2,500. That means I can set this side equal to 2,500 and then plug a 1 in for t on this side, which would give me 10,000 over 1 plus e to just the negative k now. 9e to the negative k. Okay? Now, we're going to do a little bit of work here. So I could divide both sides by 10,000. 2,500 divided by 10,000 is just 1/4. 1 over 1 plus 9e to the negative k. Take reciprocals of both sides. 4 equals 1 plus 9e to the negative k. And I'm going to do a few steps in 1 here. I can subtract 1 from both sides, so I'd get 3. Divide by 9, I would get 1/3. And that's equal to e to the negative k. Now, you could continue. You could go further and solve for k by taking a natural logarithm and all of the stuff that, you would do from there. There's really only one more step after that. I'm going to leave it in this form, though. And here's the reason why. This population growth model, if you notice, I can write it in a slightly different form if I use a useful exponent property. That e to the negative kt down there is the same thing as e to the negative k to the power of t. That's using another exponent property. So instead of solving for k, I'm just getting this e to the negative k in parentheses here, which shows up exactly here. And I know that that is equal to 1/3. So the thing in parentheses can be swapped out for just a 1/3 now. So now I know that P of t is equal to 10,000 over 1 plus 9 times 1/3 to the power of t. Notice there's no more k there. Okay? So this is my population growth model. I like this much better than what people tend to do, which is they solve for k, and then they plug that k into the growth model. The reason this is better is because if you solve for k, then you're going to end up getting a decimal that you have to round, because you're going to take a natural logarithm of 1/3. That's an irrational number. You're going to have to round that. And as soon as you round that number, this is no longer an exact value. It's an approximation. Here, no approximation is being made. I'm giving myself exact values. This is a better solution than solving for k and then rounding that decimal. Okay, so what is the final thing that we're doing here? It says, what is the population going to be after 3 years? Well, now that I have my population growth model, I just need to plug 3 in. That's 10,000 over 1 plus 9 times 1/3 to the 3rd power. I'm plugging 3 in. That's 1 over 27. 9 divided by 27 is 1/3 plus 1. That would be 4/3. So I get 10,000 over 4/3, which is 7,500 deer. And that's it. That's all she wrote on that one. Okay. I want to point something out that's going to show up in the homework just to be kind of aware of it. The homework is going to have you do some things with the logistic model as well. And one of the things it's going to ask you to prove is that the maximum rate of growth occurs when we're exactly halfway to our carrying capacity. So your population is increasing towards that carrying capacity as time passes, the whole time. But the rate at which it's increasing will speed up or slow down. And there's a problem that asks you to show, by using the differential equation directly, that the fastest rate of growth happens at exactly half of that carrying capacity, which in this case would be at 5,000 deer. So once our population hit 5,000 deer, which would have been a time before this, we would have seen the fastest growth rate in our population, and then after that it would have started slowing down. Okay, so I'm just mentioning that just to give you a heads up on what's coming, but that's really everything we need to talk about in 9.4.